Hello everyone. Welcome back to the AWS Certified Solution Architect Associate Certification Bootcamp. In this session, we'll explore Classic Load Balancer or CLB, Network Load Balancer or NLB, and Gateway Load Balancer as GWLB. Before we begin, let's review the content we are planning to cover in this session. We'll start with Classic Load Balancer. Classic Load Balancer is a legacy load balancer and AWS does not recommend you to use Classic Load Balancer. We will also cover why you should not use Classic Load Balancer and rather use ALB or Network Load Balancer. Then we will move to Network Load Balancer and we will cover Target Groups, TLS Offloading and TLS Pass-through. Then we will focus on Zonal Isolation and cross-zone load balancing for Network Load Balancer. Followed by, we'll move to Gateway Load Balancer. We'll review Gateway Load Balancer target groups and then we'll review connection draining. Connection draining, also known as deregistration delay in Application Load Balancer and Network Load Balancers. We'll also do a side-by-side comparisons between these load balancers and you will also learn their differences, use cases, features and when to use them. We have a lot to cover. Let's jump right into it. Classic Load Balancer or CLB is the original AWS load balancer that operates at both layer 4, which is TCP, and layer 7, which is HTTP and HTTPS. It is now considered as legacy and not recommended for any new application. But AWS loves to test CLB concepts for at least one question, especially backend compatibility during AWS Certified Solution Architect Associate certification. Classic Load Balancer or CLB can distribute traffic across multiple EC2 instances and support both basic health check, SSL termination, and sticky session using cookies. Now let's review why you should not use Classic Load Balancer for new generation application. Although Classic Load Balancer works with layer 7 traffic, but it lacks advanced routing features like host-based or path-based routing, which are available in Application Load Balancer or ALB. It does not support IP-based targets or container-based workloads and lacks new features like WebSockets or HTTP2. That is why AWS does not recommend Classic Load Balancer for new workload. During the certification exam, you might come across some migration scenarios or when you are dealing with older applications that have not been modernized yet. For those cases, you should only select Classic Load Balancers. Now let's review Network Load Balancer. Network Load Balancer is a layer 4 load balancer and it operates at the TCP and UDP level. Network Load Balancer is designed for extreme high performance and low latency. If your application needs to handle millions of requests per second or high throughput TCP traffic, Network Load Balancer is your go-to choice. Unlike Application Load Balancer, you can assign elastic IP to the Network Load Balancer, or you can use AWS provided static IP per availability zone, which is great for whitelisting IPs or legacy applications that require fixed IP address. In terms of supported target types, NLB supports EC2 as backend targets. It also supports IP addresses inside or outside your VPC and also Application Load Balancer as backend target. That means you can front-end your request with a Network Load Balancer and you can create an Application Load Balancer with backend target as the target for the Network Load Balancer. Network Load Balancer supports TCP, UDP and TLS listeners. For Network Load Balancer, you can use TCP or HTTP based health checks to determine the availability of each targets. And Network Load Balancer only distribute traffic to the healthy instances or to the healthy targets. You can also specify the port for each target when you are doing the port mapping and which will allow multiple services on different ports in the same instance or IP address. This is a big advantage for Network Load Balancer. Now let's review TLS offloading. Network load balancer supports TLS termination at layer 4 using TLS listener, and these offloads the encryption decryption work from your backend servers. Network load balancer also supports TLS pass-through. Now let's understand both the concepts with diagram. Let's assume we have a network load balancer in front of our backend targets, which could be EC2 instances, and the client is sending encrypted request over port 443. Now you can configure a TLS target group with port 443 to forward the traffic to the backend targets. Since you are configuring TLS target group over port 443, network load balancer will first decrypt the user request, then it will open another one new TLS session and encrypt the request, and it will pass that encrypted request to the TLS target group, which is our Amazon EC2. Then Amazon EC2 will decrypt the request before processing. You have the option to create TCP target group over port 80. If you are creating TCP target group over port 80, the network load balancer will accept the encrypted request, it will decrypt the request, and then it will pass the encrypted request over port 80 to the TCP target group. You can also configure TCP target group on port 443, and since port 443 supports SSL or TLS, in that case network load balancer will not perform any encryption or decryption at the network load balancer level. It will pass through the encrypted traffic directly to the backend server, which is called TLS pass-through. Please remember, for TLS offloading, you have to create TLS target group at port 443, and for TLS pass-through, you need to create TCP target group at port 443. If you are creating TCP target group at port 80, then your backend target will receive unencrypted traffic. Now let's review multi-AZ support. Network load balancer can be configured to operate across multiple availability zones within an AWS region, and AWS recommends customers to configure load balancer and targets in multiple availability zones for achieving high availability. Automatic failover will occur if one availability zone becomes unhealthy. The network load balancer automatically redirects the traffic to the healthy availability zones. In our current example, you can see, and we have assumed that USTist 1A is not available. That means this availability zone is not healthy. That is why network load balancer will stop sending traffic to this availability zone, and it will route traffic to the nearest healthy availability zone. There is also a concept called zonal shift, and in that case network load balancer automatically fail over to other healthy availability zone. Let's understand with a diagram. Let's assume you have enabled network load balancer only to one availability zone and you are serving traffic across availability zones. Your architecture diagram looks like this. Now in USTist 1, if the network load balancer service alone is not working, or if there is an outage only to the network load balancer, in that case AWS will automatically fail over the network load balancer to a nearest healthy availability zone, in our example to USTist 1B, and all your backend targets will receive traffic from the failed over network load balancer instance. Now let's review cross-zone load balancing. By default, each network load balancer node distributes traffic across the registered targets in its availability zone only. Now, if you have zone imbalance, which is shown in our example, that means you do not have equal number of targets in every availability zone, then some backend targets can be idle while others can be intensively working. In our example, let's assume USTist 1A has 2 targets, USTist 1B has 3 targets, whereas USTist 1C has only 1 target. Let's assume a request volume of 18 requests per second. Without configuring cross-zone load balancing, the 18 requests will be evenly distributed among the NLB nodes in each availability zone. Every NLB instances in an availability zone will receive 6 requests. By default, NLB distributes the traffic evenly among the healthy targets in that availability zone. As a result, every EC2 target in USTist 1A availability zone will receive 3 requests. Targets in USTist 1B will receive 2 requests each, whereas the target in USTist 1C will receive 6 requests. From this example, you can understand that a target in USTist 1C is processing more requests per second than targets in USTist 1B. Now, if you turn on cross-zone load balancing, each network load balancer node distributes traffic across the registered target in all enabled availability zone. Let's understand with an example. In this diagram, we have enabled cross-zone load balancing, and you can see every network load balancer instance is distributing traffic to all the targets across availability zone, and that is why all the backend targets will receive 3 requests per second. You can also turn on cross-zone load balancing at the target group level. Let's review another one feature of network load balancer, which is preserve source IP address. Network load balancer has the capability to preserve the source IP of the client. Let's understand with an example. Let's assume our client IP is 10.10.100.120 and this is a private IP. Our client is trying to access the backend EC2 using the network load balancer. In case of application load balancer we have reviewed, the backend target will always see application load balancer's private IP, and that is why we have X forwarded for, X forwarded proto and X forwarded port. However, for network load balancer, preserve client IP is by default enabled, and once that is enabled, the backend target will see the client IP rather than network load balancer's private IP. As I mentioned, client IP preservation is enabled by default, and here is the configuration. When you are creating the target group, you might not see the traffic configuration. However, to toggle this configuration, once you have an existing target group, you can edit the target group and you can toggle that switch. Now let's move to Gateway Load Balancer or GWLB. Gateway Load Balancer is designed for developing, scanning and managing third-party virtual appliances like firewall, intrusion detection systems, deep packet inspections or traffic monitoring tools. Gateway Load Balancer operates at layer 3, which is OSI network layer, and it uses GNEV protocol on port 6081. Please remember GNEV protocol and port 6081. If you have any questions with these two terminology, it is referring to Gateway Load Balancer. Gateway Load Balancer sits between your VPC and the internet or between VPCs, so you can inspect all the traffic. Let's understand using this diagram. Let's assume we have third-party appliances and we are not using AWS native firewalls, rather we are using firewall solution like Palo Alto. You can configure Palo Alto using EC2 instances, and we are using multiple availability zones for high availability. Now your gateway load balancer will sit in between the network connection and the firewall, and gateway load balancer will distribute the traffic among those EC2 instances or the firewall instances. Gateway load balancer routes traffic to the virtual appliances without changing packet header. It can also perform the auto scaling for the appliances, and gateway load balancer can add or remove appliances based on their load. Please remember, gateway load balancer provides GNEV encapsulation, which means it allows passing metadata like source IP, destination IP, and original headers along with the traffic for deep inspection, and it does not alter these attributes. In terms of supported target types, gateway load balancer can have target group consist of EC2 instances running your security appliances, or you can also have private IPs as your target. For AWS Certified Solution Architect Associate exam, please remember Gateway Load Balancer is not for balancing HTTP or HTTPS request. You should use Gateway Load Balancer only for security, inspection or network analysis, not for any content routing. And please remember GNEV protocol and port 6081 because these are the two terms which you are very likely to see during your certification exam. Now let's review connection draining or deregistration delay. Connection draining is a feature in Elastic Load Balancer which ensures in-flight requests are completed before an EC2 instance is deregistered or become unhealthy. Let me explain with a simple real-life example. Imagine that you are at a restaurant and the kitchen is about to close. Now connection draining is like the staff is saying that we won't take new orders, but we will finish cooking the meals that is already ordered to us. Elastic Load Balancer connection draining also works like that way. Elastic Load Balancer only route traffics across the healthy instances, and let's assume that we have 3 healthy targets in our target group. Now every request might take seconds to process. But let's assume you have some process, maybe a database query which is taking more than some seconds and it is taking tens of seconds. In between, the EC2 instance is not responding to the health check. That means the connection went to fetch the database and your EC2 instance is not responding. In that case, if the Elastic Load Balancer marked that EC2 instance as unhealthy, then the client request which was processing in that EC2 instance will be lost and client will get error. To prevent that, connection draining will come into picture. You must be thinking, what are the scenarios? In what scenario a target group can go rogue or it is not responding or it is become unhealthy? Out of many scenarios, here I have listed couple. The first could be your auto scaling is removing an existing instance and that time maybe the instance is processing some in-flight client request. Also an existing instance failed health check, or maybe you are running some in-place deployment while you are serving production traffic and an existing EC2 instance can be replaced with an updated version of the software. In those cases, the target group can be marked as unhealthy. When the connection draining is enabled, the ELB stops sending new requests to that instances, but it will allow existing connection to finish. And you can configure this timeout duration. The default duration is 300 seconds and you can configure this from 0 to 3600 seconds. Please remember, even if you have enabled connection draining and if the request does not complete in that time, then that connection will be closed. And why it is important? It prevents users from getting error during instance termination or scaling event. It also ensures a smooth experience during deployment, scaling, or even for maintenance. Now let's compare every Elastic Load Balancer side by side and let's review their features. In terms of operation layer, Classic Load Balancer works on layer 4 and layer 7. Application Load Balancer works on layer 7. Network Load Balancer on layer 4 and Gateway Load Balancer works on layer 3. In terms of advanced routing, only ALB supports advanced routing like host-based, path-based, IP-based routing. All other load balancers does not support advanced routing. In terms of TLS termination, Classic Load Balancer, Application Load Balancer and Network Load Balancer support TLS termination. Gateway Load Balancer always pass through the request and it does not support TLS termination. In terms of static IP support, only Network Load Balancer and Gateway Load Balancer support static IP, other two does not. When it comes to cross-zone support, for Classic Load Balancer, it is disabled by default. For Application Load Balancer, it is always enabled by default. Network Load Balancer and Gateway Load Balancer, that is disabled by default. Once you enable cross-zone load balancing, that means you are sending traffic across availability zones and AWS charges for that. For classic load balancer, there is no charge, although it is by default disabled. If you enable cross-zone load balancing, classic load balancer does not charge. Similarly, application load balancer. However, for network load balancer and gateway load balancer, they are disabled by default. But if you enable, you need to pay the data transfer fee between availability zones. In terms of use cases, classic load balancer can be used for legacy apps, application load balancer for all web applications where you need to handle layer 7 traffic, network load balancer for IoT applications, gaming applications, or for applications where you need to handle millions of requests, and gateway load balancer for third-party applications like firewalls, intrusion detection systems, deep packet inspection systems, or traffic monitoring tool. In terms of target types, CLB supports only EC2 instances, application load balancer support EC2, ECS, IP address, Lambda function, network load balancer support EC2 instances, IP address, and application load balancer. Gateway load balancer supports only EC2 and IP address. Now let's review the network load balancer and the gateway load balancer configurations. Back to my AWS management console, and I am at EC2 dashboard. Now under load balancings, I'll go to load balancers. I'll create load balancer. We already reviewed this screen. We have different options. Let's start with network load balancer. Although we are not going to create that, we are just going to review these options. The basic screen is same. You need to start with a load balancer name. You can create either for internet facing or for an internal load balancer. Let's go with internet facing. Load balancer IP address type, either you can use IPv4 or dual stack, that means IPv4 and IPv6. I'll go with IPv4, that is the default option. In terms of network mapping, let's select the default VPC. In terms of availability zone, you can select multiple availability zones. For this demo, I am using AP Southeast 1 or India Mumbai region. That is why I have only 3 availability zones. Now here you can either assign IPv4 address assigned by AWS, or you can use an elastic IP address. Since I do not have any elastic IP address, that is why elastic IP option is disabled. But once you will have elastic IP which is not assigned to anything, you will see this option will be enabled. In terms of security group, like application load balancer, you can create the security group and you can attach here. Then the listeners and routing configurations. In terms of protocol, you can either create TCP, TLS, UDP and TCP UDP protocols. And in terms of port, here you can assign port 80, 443 or any custom port. Now let's create a target group first. This target group creation, this is common for all the elastic load balancers. That is why you can see instances, IP address, Lambda function and application load balancer. Now let's create this target group. I'm going to provide the name CES NLB Target Group or TGT. Protocol I can use either TCP, HTTPS, and you can see although network load balancer does not support HTTP and HTTPS, since this is a common screen, that is why you can see all those possible options. GNEV is only for gateway load balancer. TCP, TLS, UDP, TCP, UDP, this is only for network load balancer. HTTP and HTTPS, that is only for application load balancer. Since we are creating for network load balancer, let's choose TLS. Port will be 443. In terms of IP address type, I'm fine with IPv4. We can go ahead and configure health check. NLB supports either in TCP or HTTP, HTTPS. Let's go with HTTP and you can provide that health check path, or you can go with /. In terms of advanced setting, we have already reviewed the configurations of healthy threshold, unhealthy threshold, timeout, intervals and success code. I am not going to modify anything and I am going to click next. In the next screen, we have to register our targets. Currently, I do not have any EC2 instance running in Asia Pacific Mumbai. That is why you won't see any registered targets or targets to be registered. Let's create the target group without any registered target. Our target group is already created. We do not have any backend target, that is why healthy 0, unhealthy 0. Let's go to target group and let's review the other parameters or other configurations. I'll go to target groups. I'll select the target group. From action, I am going to edit target group attributes. Now here are the options you are going to see which was not available while creating the target group. Here is the option for target deregistration management or the target deregistration delay. If you want to enable connection draining, then you need to enable this, and the default registration delay is 300 seconds. However, it supports from 0 to 3600 seconds. Here is the traffic configuration. Preserve client IP address is enabled by default. However, you can toggle that. I'll go with the default option. Here is your session stickiness. You can also enable the stickiness and you can turn on that stickiness. You can use the cross-zone load balancing also. Either you can use inherit settings from network load balancers. You can either make it on or you can totally turn off cross-zone load balancing. There is no other configurations, so let's save changes. Here we have one error. You cannot enable stickiness on target group with TLS protocol, which is absolutely correct. Although we have enabled stickiness, but this is network load balancer which does not work with HTTP and HTTPS. We have created a TLS listener, that is why this error. So I have checked off, and now let's save changes. Here you go. My target group has been updated successfully. If you want, you can browse different options. You can go and check different options or configurations for gateway load balancer. However, I am going to delete this target group. I do not have any backend targets. And to delete that, I'll go to action, delete. I'll confirm delete. Now my target group has been deleted. That wraps up this module. If you found this video helpful, please give it a thumbs up and subscribe for more AWS exam preparation courses and cloud certification bootcamps. Got questions or feedback? Drop them in the comment. We love to hear from you. Thanks for learning with us at Cloud Expert Solutions. You are now one step closer to crushing your exam. See you in the next module.